Welcome to the Deep Dive, your shortcut to mastering complex science. Today, we are strapping in for an exploration of numerical relativity, the field that's all about solving, well, probably the most notorious equations in all of science. Einstein's field equations.
It's absolutely essential work.
Yeah.
General relativity is the bedrock of cosmology and black hole physics. But here's the catch.
There's always a catch.
Always. The problem is that clean, exact mathematical answers, analytical solutions, they only exist for a few really idealized cases. You need perfect symmetry, like a spherical star or a single non-spinning black hole.
Right. And the real universe isn't clean or symmetrical. If you want to model anything that actually looks like the messy, dynamic stuff out there, like two black holes spiraling into each other, you just hit a wall.
You do.
So our mission in this deep dive is to shortcut you past decades of, let's be honest, mathematical failure, to get to the breakthroughs that finally let physicists simulate these critical, strong field systems.
And this is so important. For decades, GR was basically untested in that strong field high-velocity regime. Numerical relativity. It's not just for making cool movies. It generates the actual waveforms, the templates, the detectors like LIGO use to see the universe. It's the only testing ground we have for strong gravity.
Okay, so let's unpack that core problem. General relativity is a four-dimensional theory of space-time. You can't just, plug that into a computer program that thinks step by step in time. So how do physicists do it? How do they turn that 4D reality into a time problem?
The key is a mathematical trick. It's called the 3+1 Arnowit-Desarmesnir decomposition, or just ADM.
The ADM decomposition.
Right. It's all about recasting this incredibly nonlinear four-dimensional system into a form that a computer can handle, basically an initial value problem.
So that loaf of bread analogy you hear sometimes, that's what this is.
That's exactly it. You take the 4D space-time and you slice it. You slice it into a continuous stack of 3D space-like surfaces, your time slices. And these slices stack up along a one-dimensional time axis.
And that separation of space and time is what lets you define the state of the universe at one specific moment.
Precisely. It lets you isolate the variables that define the gravitational field at, say, time equals 0.
And when you do this mathematical slicing, what kind of equations pop out? It can't all be one thing.
No, you get two very different types. First are the constraint equations, the Hamiltonian and momentum constraints. Think of these as the rules of the game. They tell you what conditions the gravitational field has to satisfy on any single slice of time.
So they're the setup rules for your starting line for T0.
Exactly. But then you have the second set, the evolution equations, and their job is to describe how the geometry changes, how you get from one slice to the next.
Okay, that sounds straightforward enough. Why couldn't they just use this ADM system right away to simulate black hole mergers?
Because it was a disaster. The original formulation, it led to simulations that crashed almost instantly.
Why? What was wrong with the math?
It's a deep issue with mathematical stability. The original ADM system was only what's called weakly hyperbolic.
And what does weakly hyperbolic mean when you're running a simulation?
It means it's ill-posed, which in practice means that any tiny high-frequency errors, and you always have tiny errors in a computer just from rounding numbers, they don't stay small.
They grow.
They grow exponentially. So the numerical noise, the garbage, just completely floods the physical signal. The simulations were useless. This one flaw basically paralyzed the entire field for decades.
So we've established that you need a perfectly stable starting point, one that nails those constraint equations. That sounds incredibly hard if your starting point is something as wild as two black holes orbiting each other.
Oh, it is. Constructing initial data is practically a whole field by itself. The data has to satisfy the constraints, period. So a couple of major approaches were developed to model these quasi-equilibrium states.
Such as?
Well, the first is the conformal transverse traceless approach.
Right. People
often connect it to the Bowen-York solutions. It's really good for generating the starting data for two black holes that you assume are already in a nice, stable circular orbit.
It gives you a clean start.
It does. And the second approach is the conformal thin sandwich, or CTS method.
CTS.
Yeah. It's also designed for quasi-equilibrium, but it's really useful because it lets you set specific boundary conditions right on the black hole horizons themselves, defining their spin and velocity much more precisely from the get-go.
Okay, so we have these numerical black holes set up. How do we know what we're actually looking at? How do we measure their properties in the simulation?
We tie them back to the exact solutions we do know. The most general stationary black hole is the Kerr-Newman metric. And the beauty of it is that it's completely defined by just three numbers: mass, angular momentum, and charge.
So those are the physical properties we're tracking.
Right. And for a rotating black hole, that total mass, m, isn't just one monolithic thing. It has parts.
Okay.
For a Kerr black hole, the mass is composed of the irreducible mass, plus a contribution from its rotational kinetic energy. Now, the irreducible mass is proportional to the area of the event horizon.
And that leads to the area theorem, right?
Exactly. Classically, the area of the horizon, and therefore the irreducible mass, can never decrease. That's huge. It means you can only ever extract energy from the rotation, from the spin.
So if two spinning black holes merge, you can't touch their combined irreducible mass. The only energy available to be radiated away as gravitational waves is coming from their spin and orbital energy.
Precisely. It's a fundamental conservation law for the area, and it sets a hard limit on the energy output.
Okay, but dealing with the singularity, that point of infinite density, that sounds like the ultimate computer killer. If that thing hits your numerical grid, the whole simulation just has to fail.
It does. And handling the singularity was, the great crisis of numerical relativity. It took decades. There were basically three main strategies.
What's the first?
The first was using singularity avoiding coordinates. The idea is you choose your coordinate system, say, using a technique called maximal slicing, to dynamically warp the spatial slices so they literally never touch the event horizon.
So the singularity is always just outside the part the computer is actually working on?
Yes. The second approach is a bit more aggressive. Black hole excision.
Excision, like cutting it out.
Literally.
Right.
You just remove the black hole interior from your computational grid. And you can do this because the inside is causally disconnected from the outside. What happens inside the horizon can affect the space-time you're trying to evolve.
But both of those methods sound tricky, especially if the black holes are moving around really fast.
They are. And that leads to the third approach, which was the massive, massive breakthrough that finally solved the problem for good. The moving puncture method.
The moving puncture method. This was the one that finally let them simulate the full in-spiral and merger.
The whole thing, from start to finish, without the code crashing. It was a revolution, around 2005.
So what was the secret? What made it work?
It was a combination of two key things, a stable set of equations and very, very clever coordinate choices. The equations are called the BSSN formulation.
BSSN, named for Baumgart, Shapiro, Shibata, and Nakamura. How is it better than the old unstable ADM?
It's clever. Instead of just evolving the raw metric components, BSSN evolves several other auxiliary variables alongside them, the main one being the contracted Christoffel symbols.
And why does that help?
Because by doing that, BSSN actively works to keep the constraint equations satisfied. It prevents those little high-frequency numerical errors from building up and causing the whole thing to go unstable. It tames the beast that killed the original ADM codes.
So BSSN cleans up the physics equations. What about the puncture trick? How does that work?
That's all about the coordinates, or what we call the gauge conditions. The trick lets the singularity, the puncture, move freely through the grid. And it does this using two specific conditions. First, 1 plus log slicing for the lapse function, alpha.
What does that do?
It's a hyperbolic condition. In simple terms, it stops the time slices from crashing into each other or bunching up, which is a common way for simulations to die. And second, you use the gamma driver condition for the shift vector.
So you put it all together.
You put it all together, and these dynamic gauge conditions are engineered to let the singularity move, but they warp the coordinates around it so it never ever lands on a discrete grid point. It's an incredibly elegant solution.
Now, all of this is critical, but numerical relativity isn't just about empty space. It has to model matter, right? Things like neutron stars. How do you plug matter sources into Einstein's equations?
You do it through the stress-energy tensor, TE-days.
Yeah.
That tensor basically accounts for all sources of energy and momentum except for gravity itself. We just project that tensor onto our 3D slices, and that provides the source terms for the gravity equations.
So for something like a neutron star, what are you plugging into that tensor?
For a fluid star, we use hydrodynamics, HD, and you need what's called an equation of state, or EOS, to describe how pressure relates to density inside the star. Often we use simple models called polytropes.
Polytropes.
Yeah. So for a lower mass neutron star, you might use an NN32 polytrope, which models non-relativistic degenerate matter. If it's more massive, you might use an N33 polytrope for the ultra-relativistic case. These are crucial for studying binary neutron star mergers.
And what about when you add magnetism, which you pretty much always have to do in astrophysics?
Then you need magnetohydrodynamics, MHD. This is essential for modeling things like accretion disks around black holes or the cores of massive stars. We usually start with the ideal MHD approximation.
And what does ideal mean here?
It basically assumes the plasma has infinite electrical conductivity. And that's actually a really good approximation because astrophysical plasmas are so hot and dense that their conductivity is, for all practical purposes, infinite. It simplifies the math a lot.
I thought the modeling of collisionless matter was fascinating, like the stars in a star cluster. What did that teach us about how supermassive black holes might form?
All right, so collisionless matter is modeled using something called the Liouville equation. You're basically tracking thousands of individual stars moving on their own paths. And these simulations uncovered a mechanism for supermassive black hole growth called the avalanche effect.
The avalanche effect. Tell me about that.
So if a dense star cluster core collapses to form a seed black hole, that hole starts growing incredibly fast. It eats the low angular momentum stars nearby, but as it does, it gravitationally slingshots other stars around. This reshuffles everyone's orbits in a cascade.
An avalanche.
An avalanche that funnels more and more stars toward the center, feeding the black hole way faster than anyone thought possible. It's a potential solution to how supermassive black holes got so big so early in the universe.
And when you're building these incredibly complex codes, what's the gold standard test you always run to make sure they work?
It's the Oppenheimer-Snyder solution, the OS solution. It's the exact analytical solution for the collapse of a perfect spherical dust cloud into a non-spinning Schwarzschild black hole. Since we know the exact answer, it's the perfect benchmark to calibrate your code before you try to tackle something messy like a binary merger.
So, after all the mathematical slicing, the BSSN stabilization, the clever gauge choices, and the complex matter modeling, what's the big payoff? What do these massive simulations actually give us?
The payoff is understanding the most powerful sources of gravitational radiation in the universe. That means our models of compact binaries, binary neutron stars, binary black holes, and the mixed systems.
And we know the basic theory behind gravitational wave emission is rock solid.
Oh, absolutely. We've known for decades that gravitational waves carry away energy, causing the binary's orbit to shrink. The Hulse-Taylor binary pulsar confirmed that perfectly. But numerical relativity gives us the detailed waveforms for that final violent plunge and merger, the part that LIGO and Virgo can actually detect.
And what happens right after that merger? I know the simulations predicted a really unexpected outcome.
One of the biggest ones is black hole recoil, the kick.
A kick.
Yeah. If the merger is asymmetric, say the black holes have unequal masses, or their spins are misaligned, then the gravitational waves aren't emitted evenly in all directions.
So it's like a rocket.
It's exactly like a rocket. The anisotropic emission gives the final merged black hole a massive kick, a recoil velocity.
How massive are we talking?
We're talking thousands of kilometers per second. I mean, fast enough to eject the newly formed black hole from its own host galaxy entirely. The simulations predict there could be countless rogue, supermassive black holes flying through intergalactic space.
That's an incredible image. And finally, what do gravitational waves tell us that traditional astronomy with light never could?
It gives us something we call stellar spectroscopy, but in the gravity domain. Gravitational waves give you direct, clean measurements of the most fundamental parameters, the masses and the spins of the object.
And that's so valuable because
Because it completely avoids all the messy, complicated physics of accretion disks and gas and turbulence that obscure our view with telescopes. It's a direct window into pure, strong field gravity at work.
it's just incredible to trace this whole journey. To unlock black hole mergers, physicists had to first slice up Einstein's 4D theory into a 3+1 time problem. Then they had to fight for years with these mathematical instabilities before the BSSN formulation came along.
Yeah, numerical relativity really provides the toolkit from that initial 3+1 split all the way to the moving puncture gauge to finally explore a part of the universe that was completely off limits to analytical math. It brought GR into the computational age.
And as we went through this deep dive, the ADM decomposition, the BSSN system, the choice of the 1 plus log lapse, and the gamma driver shift, it becomes really clear that this whole enterprise depends on these choices about coordinates about the gauge.
Precisely. The choice of gauge conditions, those arbitrary functions, alpha and beta, they define your coordinate freedom. And here's the really provocative thought that comes out of all this work. The difference between a simple, obvious gauge, choice like geodesic slicing, which makes simulations crash instantly, and the highly specialized 1 plus log-gamma driver slicing, which lets them run stably for years. That difference is profound.
Meaning that?
It shows that selecting the correct stable coordinate frame isn't just a matter of convenience in general relativity. It is just as fundamental to successfully simulating nature as getting the physical laws themselves right. The choice of coordinates isn't incidental. It actually defines what is physically computable.